Okay, today what we're going to talk about is what all this means. Alright, over the last couple of days we've learned how to do indefinite integrals and definite integrals. Difference between indefinite integrals and definite integrals is that one of them gives you the bounds, the other one doesn't. Okay, if you have the bounds, there's no need for the plus c at the end. If you don't have the bounds, you do need that plus c. That's the only difference on them. We will talk more about that a little bit later, but realistically this is just because, well, we don't know where we're starting and where we're ending. There might be some constant that is being left out. Now what I want to talk about is what it means. Alright, now basically let's say that we've got a graph. Let's say that we have a velocity versus time graph. So I'm going to erase this part off of here because we're not worried about time before time is 0. But let's say that we've got a graph that looks like this. As you can see, the velocity is constantly increasing. In other words, we have an acceleration. If we were to take the derivative of this, you'd be able to figure out what the acceleration would be. Now basically, integration is the opposite. That's not good. Integration is the opposite of derivatives. That's why some people call it an antiderivative. Now in this case here, if we were to take the derivative of this with respect to time, we would end up with the acceleration. In other words, the derivative is going to tell us the slope. Now, literally, as you take the derivative of velocity, you get acceleration. The thing is here, if you get the opposite, if you take the integral of velocity with respect to time, you're going to get your position, or actually it's going to end up being your total distance traveled. Right? That's where this stuff becomes functional, because sometimes you don't have this straight little line here. Because of that, you're going to end up with some different stuff, and it might become functional to use this stuff here. Okay? Now, here's the difference between algebra-based and calculus-based. Now, if we had this nice, pretty straight line here, I know every single one of you could determine exactly how much area there is between the x-axis here and this triangle by just simply solving for the area of a triangle. In this case, the area is 1/2 of the base times the height. So, in this case, yeah, it's pretty simple. Now, the thing is, if you get a situation like this, such as a car shifting gears or something along those lines, you don't exactly have that nice, pretty little triangle that you had here. Now you got some crazy curves, and that means it's not going to work out perfectly using the algebra. That's where this comes in. Now basically, when you learn this in calculus class, they're going to teach it to you based upon this general theory. Alright, so let's say I'll put that same graph up here, or at least something fairly similar. Okay, now it's easy to figure out the area. The area is literally the base times the height. But when you have one of these crazy curves, it's a little bit more difficult. Through calculus, what we're doing is we're taking and determining the area of a small chunk. Let me do it in a different color so you can see it a little bit better. We're going to determine the area that is bound by this chunk right here, and then the area that is bound by this chunk right here, then the area that is bound by this chunk right here. Now if you notice what's going on here, obviously there's a little bit that is being added in that is addition to what we need. Right? These corners that I'm filling in right now, these are not under the curve. Okay? But basically this is what we are doing. We're taking a set value along the bottom and using that set value, which we are going to call dx to figure out how much area is under that curve. The area is just simply the length times the height. Now, because this is some type of a function of t, so we'll call it velocity as a function of time, that means that every single second this velocity is going to be changing. So what we're doing is we're literally finding the area by taking each individual time frame. Alright, so every single time we're taking a single area, which is the overall velocity times the little tiny chunk of time that we got here. Alright, I apologize, this should be a t here. Okay, now the nice thing about this dt, well, technically what I've drawn here instead of dt is a delta t. This means it is some significant area. dt means that we're talking about a time frame that is so infinitesimally small that it works for just a single solitary point in time. So instead of doing it like this, what it actually ends up being is something a little bit more similar to this. Each individual time frame is representing, I'm going to do this in different colors so you can kind of see it here. Each individual time frame is representing just a single instant in time. So therefore we're not getting this overlap that we had up here. We're just simply going right underneath the curve. Now by doing this, it's able to give us exactly, precisely the amount of space that's under that curve. Right now, I know this is kind of a little bit high-end, a little bit far off compared to some of the stuff that we've done in the past. So what I want to do is I want to prove this to you. So in other words, I'm going to give you this homework assignment. All right? You're going to look at a couple of different situations here. You're going to look at the integral of x. Let's do it the same format that I did before. The integral of v, we'll go v d. Alright, you know what? Hey, forget about the physics for right now. Instead of worrying about the physical concepts and the physical content, let's just do the integral of x dx. You're going to do the integral of 2 dx and the integral of 2 plus x dx. Now, if I were to look at a graph of x dx, this would be my graph. Because my y value is going to exactly be what my x value is. So when x is negative 4, y is negative 4. Negative 3, negative 3, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, 3, 3, and so on. Okay? Now, what I want you to do is use some different limits for this one. We're going to do these as definite integrals. And what I want you to do is prove that the integral works. Basically what you're going to do is you're going to algebraically solve for the area, and you're also going to use calculus. You're going to use the integration. Now, to give you an example of this, we're going to go from negative 1 to 1. Okay? So, integral of x dx. So I'm going to take the exponent, add 1 to it. So, x squared, take that new exponent, put it on the bottom, and I'm going to go from negative 1 to 1. Alright, pause. Sorry about that, had a little bit of a glitch walking in the room here. So anyway, okay, we've got x squared over 2 from negative 1 to 1. So it's going to be final minus initial. So 1 squared over 2 minus negative 1 squared over 2. 1 squared is 1, 1 over 2 is 1/2. Negative 1 squared is positive 1, positive 1 over 2 is 1/2. 1/2 minus 1/2 is 0. Okay, so what I should find is the area between this curve and the x-axis should be 0 if I go from the span of -1 to 1. So if I go from -1 to 1, alright, I've got this side is going to be 1 long, this side's going to be 1 long. 1 times 1 times a half. 1 times 1 is 1. 1 times a half is 1/2. But this 1/2 is below the x-axis. I'm going to call it negative. 1 times 1 is 1. 1 times 1/2 is 1/2. This is a positive 1/2. So if I've got an area of negative 1/2, an area of positive 1/2, negative 1/2 plus 1/2 equals 0. So all you have to do is just prove these definite integrals. Now, to show you what's going on here, to give you the basic graph for each so that you're not struggling with that part. Graph of integral of 2 dx. Well, graph of 2, x equals 2. I'm not even going to draw that one on the board. If you guys need help with it, try it on a calculator, ask your buddies, and then we'll see what happens. Now, 2 plus x dx. Once again, try it on your calculators, ask your buddies, but they are not too difficult. The things that you're going to need to know here: the area for a triangle is 1/2 of the base times the height. The area for a rectangle is base times height. And if you've got a situation where, let's say you've got a rectangle with a triangle on top, literally break it into those pieces. Put your rectangle here, triangle here, and try to calculate it out. Now, the definite integrals I want you to prove here are, we already did -1 to 1. So, also do this one in terms of -2 to 2 and 0 to 4. For this one, this one was done for you, so you do not need to do it. For this one, I want you to do this from -2 to 0, -2 to +2, and 0 to 4. Or I'm sorry, 2 dx, 2 dx. Alright, on this one here, this one you're only going to have to do a couple of times. I need you to do it from -2 to +2, and the integral, sorry, this should be in parentheses here, of 2 plus x dx from 0 to 4. Okay, so you got 1, 2, 3, 4, 5, 6, 7 of these to do. Now I want you to, number one, do the integration. The integration should not be too difficult. All you have to do is go through, work this out, and once you've done it once, you're done with all of them. The thing is, you need to go in the different ranges, and then you need to show me the proof. You need to actually graph it up. I'm going to leave graph paper back there for you, so you make sure you can get it done properly, but it shouldn't be too bad. If you have any problems, get my attention. I will have Google Messenger open up here, so if you are struggling, please send me a line, and I will be able to help you out. Best of luck to you, but now, from here on out, we're going to get into the physics realm, and it's going to be a little bit more hands-on, a little bit more active. So, get done with this part, prove that it works, and then we'll talk about what is needed in the future. Good luck.